Imagine a future where Earth, our only home, is no longer safe to live on. In this gentle thought experiment, we explore where humanity could actually go with the technology we have today if Earth became uninhabitable. From underground sanctuaries and ocean cities to distant moons and artificial worlds in space, each chapter is a scientific possibility, grounded in real engineering and research. So get comfortable, let your thoughts drift, and follow this quiet journey to the edge of survival and beyond. Chapter 1: The Last Days on Earth. For over 10,000 years, human civilization has relied on the Earth's natural systems to remain relatively stable and supportive of life. Temperature regulation through atmospheric balance, the cycling of water between oceans and sky, the availability of breathable air, and fertile soils have allowed human societies to grow from small nomadic tribes to a global species. But this delicate equilibrium is not guaranteed to persist forever. A range of natural and anthropogenic processes could push Earth's surface systems beyond the thresholds required for human habitability. This chapter outlines the main scientific scenarios in which Earth may become uninhabitable, not in the distant future, but within a time frame relevant to current or near-future generations, prompting a forced departure or dramatic reorganization of civilization as we know it. One of the most discussed and scientifically grounded reasons Earth might become uninhabitable is extreme climate change. Driven primarily by the accumulation of greenhouse gases such as carbon dioxide, methane, and nitrous oxide, Earth's climate can experience feedback loops that lead to escalating surface temperatures and disruptions to atmospheric dynamics. While the current trajectory projects a gradual rise of 2 to 4 degrees Celsius by the end of the century, more extreme scenarios show potential for runaway greenhouse effects in localized regions. These effects could make large swaths of Earth subject to lethal wet bulb temperatures, a measure of heat and humidity at which human bodies can no longer cool themselves through perspiration. Wet bulb conditions above 35 degrees Celsius are considered unsurvivable for even healthy individuals, and some equatorial regions are already reaching critical thresholds during heat waves. Simultaneously, the degradation of atmospheric composition could render breathing unsafe. Elevated carbon dioxide concentrations are known to impair cognitive performance, and airborne pollutants such as particulate matter, ozone, and nitrogen dioxide can cause chronic respiratory illness or immediate health crises. In extreme conditions, industrial accidents, volcanic activity, or war-related chemical releases could lead to local or global contamination of the air supply. Unlike temperature shifts that can be mitigated by technology, air toxicity is more difficult to escape from without complete environmental control. Another significant vector toward uninhabitability is the disruption of the global food system. Most crops are sensitive to narrow bands of temperature, rainfall, and sunlight. With changing climate patterns, fertile regions may experience persistent drought, while others face flooding and soil erosion. If global average temperatures rise just a few degrees beyond historical norms, staple crops like wheat, rice, and corn would experience substantial yield declines, especially in regions already facing food insecurity. In combination with the decline of pollinator species, salinization of irrigated soil, and loss of arable land due to urban expansion or desertification, the food web could reach a tipping point where modern agriculture can no longer provide for the global population. Beyond atmospheric and agricultural issues, access to drinkable water is also a critical factor. Over 2 billion people already live in areas of water stress, and projections show that number increasing sharply due to population growth and reduced precipitation in key watersheds. Melting glaciers, drying aquifers, and saltwater intrusion into coastal groundwater are accelerating. Even in technologically advanced countries, The infrastructure to desalinate, store, or transport water is often insufficient for full population needs if natural replenishment fails. Without a reliable source of fresh water, human settlements would either collapse or require complete dependence on energy-intensive recycling systems. In addition to biospheric disruptions, Earth's magnetic field, a shield that protects the surface from harmful solar and cosmic radiation, is not guaranteed to remain constant. There is evidence that the magnetic poles have flipped in the past, and a weakening of the magnetic field is already observable. While a full reversal could take thousands of years, any significant reduction in geomagnetic protection would increase radiation exposure, particularly at high altitudes and low-latitude regions. This could damage power grids, communication systems, and even human health, especially in areas with thin ozone layers. A similar radiation-related risk comes from solar activity itself. The sun regularly produces coronal mass ejections, CMEs, which are vast expulsions of magnetized plasma that can strike Earth and disrupt electronic systems. While most CMEs are deflected or buffered by Earth's magnetic field, an unusually powerful event, similar to the Carrington event of 1859, could disable satellite communications, GPS, and power infrastructure across entire continents. In a more extreme case, it could also compromise artificial climate controls, food storage, and water purification, triggering cascading system failures. Another possibility comes from tectonic or volcanic activity. Though Earth's crust has always been geologically active, a global-scale volcanic event, such as the eruption of a supervolcano, could plunge the planet into a years-long volcanic winter. Sulfur aerosols injected into the stratosphere would reflect sunlight and cool the surface dramatically. Crops would fail, photosynthesis would slow, infrastructure would become buried or inoperable due to ash and acid rain. Notable supervolcanoes such as the Yellowstone caldera or the Toba system in Indonesia have the capacity to produce these effects. While rare, their probability is not zero, and their impact would be immediate and far-reaching. Other risk scenarios include biological hazards. A naturally evolved or bioengineered pathogen could alter the balance of life on Earth dramatically. While diseases generally do not wipe out their hosts entirely, a highly contagious virus with high mortality, long incubation, and resistance to current medicine could incapacitate global systems. Unlike localized disasters, pandemics scale with population density and global connectivity. If multiple pandemic waves coincided with failing climate or food systems, Earth's biosphere could become uninhabitable, not in the traditional environmental sense, but in the functional, societal one. In a more technological context, global-scale technological accidents could also play a role. A widespread failure of power infrastructure, possibly due to cascading cyber attacks or AI mismanagement, could render entire societies non-functional. The loss of digital control over food supply chains, emergency services, healthcare, and clean water would not need to kill directly, only to make modern survival impossible. Once key systems fall, secondary risks like famine, exposure, and disease follow swiftly. Furthermore, while lower in probability but higher in impact, Earth remains vulnerable to near-Earth objects, NEOs, such as asteroids or comets. Planetary defense systems are currently limited to tracking and early warning. While NASA's DART mission demonstrated the ability to slightly redirect an asteroid, the global infrastructure for rapid response or deflection of large objects is still in its infancy. An impactor larger than 1 kilometer could cause regional destruction, megatsunamis, and atmospheric fallout. If larger than 10 kilometers, like the asteroid linked to the Cretaceous-Paleogene extinction, global habitability would be at serious risk. It is also worth noting that large-scale uninhabitability does not require a single catastrophic event. A combination of moderate but compounding stressors, such as resource scarcity, migration pressure, ecosystem collapse, and civil unrest, could render the Earth functionally uninhabitable by degrading quality of life below survivable standards. Even if parts of the biosphere remain technically livable, the inability to maintain global cooperation and infrastructure could break down continuity of civilization and force relocation or radical decentralization. In all of these cases, the pace of degradation matters. A slow decline gives time for mitigation strategies. A rapid cascade of failures would not. Scientists and engineers continuously develop early warning systems and predictive models to anticipate critical thresholds. But response planning is limited by available resources, global coordination, and political stability. Thus, the decision to leave the surface of Earth would not be taken lightly. It would follow not from a singular decision, but from a growing sequence of data points, predictive models, and lived experience, indicating that the environmental, atmospheric, geological, and technological systems of Earth can no longer support sustained human life at scale. In the chapters that follow, we will explore the next steps, beginning with how humans might seek to survive beneath the Earth's surface or within its oceans, before reaching outward to the Moon, Mars, and beyond. Chapter 2. Underground Sanctuaries and Ice Caves. When Earth's surface becomes increasingly hostile to human life due to soaring temperatures, toxic air, or persistent radiation, adaptation becomes a matter of engineering, logistics, and biology. Humans have always demonstrated the ability to modify their surroundings to survive, from desert outposts to polar stations. As conditions worsen above ground, the next frontier of adaptation may lie below it. By transitioning into subsurface environments, humanity can create insulated ecosystems that are protected from many surface-level dangers. Underground facilities shield inhabitants from radiation and extreme weather, allow for controlled climates, and offer a stable platform for essential life support systems. While living underground or within ice caves presents unique engineering and psychological challenges, current and near-term technology is sufficient to make such environments habitable for extended periods. Thermal stability is one of the greatest advantages offered by subsurface living. Below about 10 meters, Earth's temperature stabilizes and remains close to the average annual surface temperature of the surrounding region. This natural insulation minimizes the energy demands required to maintain internal climate control, providing a passive method of thermal regulation. In cold regions, underground habitats can capture and retain geothermal heat. In warmer zones, they offer protection from temperature spikes and heat waves that are increasingly common on the surface. Radiation shielding is another key benefit. Cosmic rays and solar particle events pose serious risks, especially if Earth's magnetic field weakens or if the ozone layer becomes depleted. Even a modest overburden of earth or rock, around 1 meter of soil or 30 centimeters of concrete, can block over 95% of this radiation. In deeper locations, such as mines or natural caverns, exposure is negligible. This makes underground locations ideal for not only habitation, but also for storing sensitive electronics, preserving genetic data, and conducting research in radiation-sensitive environments. Site selection for underground settlements requires careful geological and environmental evaluation. The ideal location will feature stable bedrock, minimal seismic activity, and access to essential resources like groundwater and geothermal energy. Many regions already have dormant or decommissioned infrastructure, such as transportation tunnels, military bunkers, and mining complexes, that could be converted or expanded into fully self-sustaining habitats. Retrofitting these spaces may be more practical than building entirely new underground cities, particularly in time-sensitive scenarios. In some cold regions, particularly near the poles or in high-altitude zones, ice caves offer an alternative to traditional subterranean structures. These caves, formed by natural glacial movements or carved into ice sheets, remain frozen year-round and can act as natural cold storage environments. Properly sealed and reinforced, they provide radiation protection, water access, and excellent thermal insulation. The ice acts as both shield and reservoir, critical for maintaining hydration and temperature control. Ventilation systems are essential to maintaining breathable air in these closed environments. Unlike surface habitats, underground shelters cannot rely on natural air exchange. Instead, air must be circulated, filtered, and refreshed using controlled systems. Technologies from submarines and the International Space Station, such as lithium hydroxide scrubbers for carbon dioxide removal and oxygen generation through water electrolysis, are well suited to underground application. Modern HEPA filters can remove particles, pathogens, and chemical contaminants from recirculated air, while redundancy in life support systems ensures that a single failure does not jeopardize the entire habitat. To remain underground for extended periods, food production must also be internalized. Hydroponics and aeroponics, methods of growing plants without soil, enable year-round agriculture in compact, vertically arranged spaces. These systems require only nutrient-rich water and light, which can be supplied by energy-efficient LEDs tuned to specific wavelengths. Crops such as lettuce, spinach, tomatoes, and herbs are already cultivated in underground farms in places like London and Tokyo. With advances in automation and genetic optimization, the productivity of such systems continues to increase. Wastewater from human use can be filtered and recycled to support crop growth, and plant matter can contribute to a closed-loop nutrient cycle. Energy supply is a critical consideration. In favorable locations, geothermal energy provides a reliable, continuous power source with a minimal surface footprint. This form of energy is already used extensively in countries such as Iceland and New Zealand, where geothermal is not viable, compact nuclear reactors, such as NASA's kilopower designs, or commercial microreactors under development in the United States and Canada, offer scalable alternatives. These reactors are designed to operate for years with minimal maintenance, making them suitable for isolated environments. In extreme cases, batteries or hydrogen fuel cells may provide backup energy during installation or emergencies. Water access underground is often more stable than on the surface. Aquifers, natural underground reservoirs, exist beneath much of the Earth's crust and can be accessed with proper drilling. These sources are less vulnerable to evaporation, contamination, or weather patterns than surface water. Where aquifers are unavailable or unsafe, water can be extracted from melted ice in frozen regions, or even generated from atmospheric moisture using dehumidifying systems in sealed environments. Advanced purification methods such as reverse osmosis, UV sterilization, and nanofiltration ensure safe drinking water and clean supplies for irrigation and hygiene. In colder regions, ice caves and glacial shelters offer both water supply and thermal efficiency. The Dachstein ice cave system in Austria, for example, has maintained structural and thermal integrity for thousands of years. With added reinforcement and internal heating, such environments could be adapted into semi-permanent settlements. Their low temperatures can also support medical storage, seed banks, and long-term preservation of materials. Waste management is another vital aspect of enclosed habitat life. Human and organic waste can be composted or processed into usable resources, such as methane for energy or fertilizer for crops. More complex waste streams, such as electronics or pharmaceuticals, require chemical treatment or secure storage. Modular waste processing units, already developed for military outposts and polar research stations, can be integrated into habitat infrastructure. Over time, recycling systems can be scaled to reduce dependency on outside inputs. Communication with the outside world, including other subterranean hubs, requires specialized infrastructure. Radio signals degrade quickly in dense rock, limiting the effectiveness of traditional antennas. Instead, Fiber optic networks and wired relay stations are used to connect underground settlements to each other and to surface-level transmission hubs. Where surface relays are vulnerable, buried satellite uplinks or drone-based repeaters can be deployed. For internal communication, localized networks ensure coordination between modules and personnel, enabling real-time monitoring of environmental systems and operational status. The psychological challenges of underground life must not be overlooked. While the focus here remains scientific, it's worth noting that humans evolved in open environments with daylight, sky, and dynamic sensory input. To counteract sensory deprivation and maintain cognitive function, modern underground design emphasizes artificial lighting that simulates natural day-night cycles, color variation in architecture, and flexible living spaces. Adjustable LED systems can mimic sunrise, daylight, and sunset. Video walls and simulated windows offer digital representations of outdoor landscapes, aiding orientation and well-being. Construction and expansion of underground shelters can be accomplished using tunnel boring machines, TBMs, a technology already used in modern subway and transportation projects. These machines can excavate large tunnels quickly and safely, and their use can be supported by robotic scaffolding systems and prefabricated module placement. In extreme or remote areas, construction drones and autonomous diggers could be deployed first, reducing risk to human crews during early development. Some nations have already explored underground infrastructure for national defense and data storage. The Cheyenne Mountain Complex in the United States, built into a granite mountain, is designed to survive nuclear blasts and remain operational for extended periods. The Svalbard Global Seed Vault, built into the permafrost of a remote island in Norway, stores genetic material from crops around the world in a secure, cold environment. These facilities are proof of concept for more generalized survival infrastructure, showing that underground systems can be maintained and secured even in hostile or unstable conditions. Ultimately, underground and ice-based shelters provide a scientifically credible option for adapting to a planet undergoing surface failure. They are not speculative technologies, but extensions of methods already tested in mining, defense, polar research, and space analog missions. With appropriate investment, coordination, and engineering, these environments can serve as transitional safe zones, offering humanity a way to remain on Earth, even as its surface becomes progressively unlivable. Chapter 3: Underwater Cities and Floating Havens. As Earth's surface becomes increasingly less hospitable due to atmospheric toxicity, rising temperatures, or extreme weather, adaptation does not necessarily require leaving the planet entirely. Another scientifically viable direction lies in the vast and underutilized domain of Earth's oceans. Covering over 70% of the planet's surface, the oceans offer both challenges and opportunities for long-term human habitation. Through a combination of submerged habitats and surface-based floating structures, it is possible to establish resilient, energy-efficient, and strategically distributed communities that are less vulnerable to the dangers facing traditional, land-based civilizations. Underwater and floating settlements offer protection from many surface-level risks. The ocean's moderate temperature extremes buffer against solar radiation and provide access to abundant water and renewable energy sources. Moreover, they offer flexibility in location. Habitats can be deployed in equatorial or polar regions, near continental shelves, or in international waters. With current technologies and infrastructure development underway in multiple countries, ocean-based living represents one of the most promising strategies for short to medium-term human survival in the face of global surface instability. The concept of living underwater is not new. Since the 1960s, experiments such as Jacques Cousteau's Conshelf series and the U.S. Navy's SEALAB program have demonstrated the viability of submerged human habitation. More recently, NASA's NEMO, NASA Extreme Environment Mission Operations project has used the Aquarius Reef Base, located 19 meters beneath the surface off the coast of Florida, as a testing ground for life in confined and isolated environments. These real-world tests provide the foundation for scaling underwater habitats into viable communities. Underwater settlements are typically built as pressurized environments. This allows internal air pressure to match surface levels, avoiding the physiological stresses associated with saturation diving. Pressurized modules are built from composite materials, titanium alloys, or reinforced acrylics, designed to withstand the ambient pressure of shallow to moderate depths. Spherical or cylindrical shapes help distribute pressure evenly, and modules can be connected through airlock tunnels or docking ports. Life support in submerged habitats includes air circulation, oxygen generation, and carbon dioxide scrubbing. Oxygen can be supplied through electrolyzing seawater or delivered via surface compressors. Carbon dioxide is removed using chemical scrubbers or solid-state filters. Wastewater is treated on-site and discharged after filtration or stored for reprocessing. These technologies are derivatives of those used on submarines and spacecraft, already field-tested and understood. Energy is typically supplied via subsea cables connected to offshore platforms or land-based grids. However, increasing attention is being paid to autonomous energy systems. Ocean thermal energy conversion, tidal turbines, and wave energy converters can supply power continuously, depending on location. Solar panels on floating platforms above the habitat can also provide supplemental energy stored in underwater battery arrays. Fresh water is readily available through desalination of seawater using reverse osmosis, multi-stage flash distillation, or electrodialysis. Modern desalination systems can produce clean drinking water with relatively low energy input, especially when waste heat from other systems is recovered. One of the most important elements of long-term underwater living is psychological stability. Extended periods in confined, dimly lit environments can impact circadian rhythms and mental health. To counteract this, modern habitat design includes full-spectrum artificial lighting, digital windows that simulate outdoor views, soundscapes, and modular furniture that can be rearranged to avoid monotony. Controlled schedules and recreational activities are essential for crew cohesion and mental well-being. Submerged habitats can support not just living quarters, but laboratories, aquaponic farms, workshops, and medical bays. Hydroponics and aquaculture systems can operate in tandem, with fish waste providing nutrients for plants and plants purifying water in return. Such closed-loop systems reduce reliance on external food deliveries and create a sustainable in-habitat food source. For protein, tilapia, shrimp, and bivalves such as mussels are popular candidates. For vegetables, leafy greens, tomatoes, and herbs grow well under artificial lighting and controlled humidity. For broader scalability and accessibility, floating cities represent another avenue for ocean-based habitation. These structures, situated on the surface of oceans, lakes, or sheltered bays, remain above water but are engineered to be resistant to sea level rise, storms, and wave activity. Floating cities offer multiple advantages. They do not require pressurization, are easier to supply and expand, and can be built using a wide variety of construction materials. Structural platforms are often based on concrete pontoons, steel frameworks, or composite flotation cells. These structures can support multi-story buildings, vertical farms, and infrastructure such as communication towers, landing pads, and water purification plants. Countries like Japan, the Netherlands, and South Korea have invested in floating infrastructure to combat land scarcity and rising sea levels. The Seasteading Institute, a US-based organization, has proposed modular floating cities designed for international waters, with decentralized governance and sustainable technology at their core. Meanwhile, Oceanic City, developed in collaboration with the United Nations Human Settlements Program, presents a scalable and climate-resilient floating city concept intended for deployment in vulnerable coastal regions. Floating settlements rely heavily on renewable energy. Photovoltaic solar panels, wind turbines, and wave energy converters can provide the majority of required electricity. Energy storage systems, including lithium-ion batteries and hydrogen fuel cells, smooth out supply and demand fluctuations. In some designs, biofuel from algae farms or waste conversion systems provides backup power. Water supply is managed through rainwater harvesting, desalination, and gray water recycling. In coastal areas, floating settlements can be connected to mainland utilities via flexible umbilical cables, but in more remote locations, complete autonomy is achieved through redundancy and modularity. Food production in floating cities is accomplished through rooftop gardens, vertical greenhouses, and integrated aquaponics systems. Unlike traditional agriculture, which is land-intensive, these methods require significantly less space and water. Biodegradable waste is composted to enrich planting substrates or converted into bioenergy. Modular architecture enables flexible city growth. Individual platforms can be added or disconnected based on population needs, maintenance schedules, or weather risks. Designs often incorporate hexagonal or radial grid patterns for maximum wave resistance and interconnectivity. Floating breakwaters, wave deflection systems, and hull stabilization mechanisms ensure comfort and safety even in rough seas. Social, educational, and commercial spaces are embedded within the urban plan, ensuring residents have access to services, healthcare, and recreation. In many designs, underwater portions of floating cities are used for ballast, storage, or submerged greenhouses that use natural light filtered through the sea surface. While ocean-based living offers numerous advantages, it must be implemented with strong environmental oversight. Ocean habitats must be built to avoid harming marine ecosystems, displacing species, or altering coastal dynamics. Non-toxic building materials, closed-loop waste systems, and minimal surface disturbance are essential. Designs must also account for storm surges, tsunamis, and long-term ocean acidification trends. Submerged habitats are often located near coral reefs, continental shelves, or thermocline boundaries for stability and accessibility. However, care must be taken to avoid damaging these ecologically sensitive areas. Environmental impact assessments and collaboration with marine biologists are critical components of habitat site selection and operation. Floating settlements are designed with extreme weather events in mind. Advanced models use weather prediction systems, reinforced mooring structures, and evacuation protocols. Some proposals include submersible platforms that can partially sink below the waves during hurricanes to minimize surface impact. Current technologies make both underwater and floating habitats feasible within short timeframes. Submerged living modules, such as those used in Nemo and commercial undersea hotels, can be deployed within months given proper funding and logistical support. Larger-scale underwater bases would take 2 to 5 years to construct and deploy, depending on depth and complexity. Floating settlements have already reached pilot stages. Individual modular platforms have been constructed and tested. Scaling these to small communities or cities is within a 5 to 10-year horizon if investment and regulation align. Governments in climate-vulnerable regions are already studying floating housing as a key adaptation strategy. These technologies are not speculative. They exist today. The challenge lies in scaling, coordinating international standards, and establishing logistical networks for supply and support. As Earth's land-based systems continue to degrade, interest and investment in marine-based living are likely to grow rapidly. Chapter 4. Life on the Moon, a harsh first step. If Earth's surface becomes uninhabitable and the oceans or underground shelters no longer offer long-term refuge, the next logical step is to look beyond the planet itself. Among all celestial bodies in our solar system, the Moon remains the most accessible. It is close enough for relatively short trips, devoid of a complex atmosphere that could hinder landings, and already a major focus for multiple space agencies. As a first step in humanity's expansion into space, the Moon is uniquely positioned to serve as a testbed for permanent off-Earth habitation. It offers both the challenges and opportunities necessary to begin building a presence beyond the planet of our origin. The Moon's average distance from Earth is approximately 384,400 kilometers. A spacecraft using current propulsion systems can make the journey in roughly 3 days. This proximity makes the Moon ideal for logistics, communication, and emergency evacuation, all of which are significant hurdles for more distant targets like Mars. Because of the short transit time, supply missions, crew rotations, and remote monitoring are more feasible than for any other body in the solar system. Moreover, real-time communication, delayed by just over 1 second, makes operations far easier than those involving distant robotic missions or future interplanetary bases. However, despite its relative closeness, the Moon is not a hospitable place. There is no breathable atmosphere. Surface temperatures vary widely, ranging from over 120 degrees Celsius during the lunar day to as much as 130 degrees at night, depending on location. A single lunar day lasts about 29.5 Earth days, meaning that any structure on the surface is exposed to roughly 2 weeks of sunlight, followed by 2 weeks of darkness. This creates complex engineering challenges for power supply, thermal control, and life support systems. The Moon is also exposed to high levels of radiation from cosmic rays and solar particle events. Without an atmosphere or magnetic field, the lunar surface provides no natural shielding. Prolonged exposure would exceed safe radiation limits for humans, increasing risks of cancer, cognitive effects, and equipment degradation. Therefore, any lunar habitat must incorporate significant radiation protection, either through heavy shielding using local regolith, buried placement within the surface, or residence in natural geological features such as lava tubes. Lava tubes on the Moon, formed by ancient volcanic activity, are among the most promising candidates for early lunar habitats. These structures can stretch for kilometers and remain stable over long periods due to the Moon's low gravity. Located beneath the surface, they offer built-in protection from radiation, micrometeorites, and temperature extremes. Accessing and sealing these tubes would be a complex task, but once achieved, they could provide the framework for permanent underground facilities with reduced construction needs and improved safety. The Moon's lower gravity, roughly 1/6 that of Earth, introduces both benefits and complications. On one hand, reduced gravity decreases structural loads and allows for more lightweight construction. On the other hand, long-term exposure to low gravity can affect human health. Studies from the International Space Station suggest that reduced gravity can lead to muscle atrophy, bone density loss, and cardiovascular deconditioning. While the Moon offers more gravity than orbital microgravity, it remains unknown how the human body adapts over months or years. Artificial gravity through rotation is impractical in early lunar bases, so mitigation strategies would likely focus on physical exercise, pharmaceuticals, and specialized medical monitoring. Life support systems for lunar habitation are based on closed-loop principles. Air must be generated and recycled, water purified and reused, and waste converted into useful products. Technologies for this are already under development and partially tested aboard the ISS. Oxygen can be extracted from water through electrolysis or directly from lunar regolith using high-temperature reduction processes. Water is a more complex issue, but evidence from orbiting satellites and landers has confirmed the presence of water ice in permanently shadowed regions near the Moon's poles. Mining this ice could provide not only drinking water, but also oxygen and hydrogen for breathing and fuel production. The availability of in-situ resources is critical to the Moon's long-term habitability. Launching all materials from Earth is prohibitively expensive and unsustainable for large populations. The ability to extract materials locally, commonly referred to as in-situ resource utilization (ISRU), is key to reducing dependency on Earth. Regolith, the Moon's dusty surface material, can be used to create building blocks, radiation shielding, and even 3D printed structures when combined with sintering techniques or binding agents. Metals such as aluminum, titanium, and iron are also present in lunar soil and could eventually support more advanced manufacturing and repair operations. Power generation is one of the most significant constraints for lunar life. Solar energy is abundant during the lunar day, but absent for roughly 2 weeks at a time. Some regions near the poles, particularly on crater rims, such as those near the Shackleton crater, receive near continuous sunlight due to the Moon's slight axial tilt. These locations are prime candidates for solar farms that can supply uninterrupted power. Energy storage systems, ranging from lithium-ion batteries to regenerative fuel cells, would be required to bridge the long periods of darkness. In parallel, compact nuclear reactors, such as the fission-based kilopower system developed by NASA, offer reliable power for shadowed or high-demand environments. Initial missions to the Moon would likely focus on modular outposts. These would include core habitation units, energy modules, life support centers, and scientific laboratories. NASA's Artemis program and associated partners plan to deploy such infrastructure beginning in the 2020s, with permanent settlement goals extending into the 2030s and beyond. The European Space Agency, China's CNSA, and private companies such as SpaceX and Blue Origin have all proposed or initiated lunar base concepts with modularity, resource utilization, and long-duration crew stays in mind. Transporting equipment and personnel to the Moon remains a logistical challenge, but is becoming increasingly feasible. The development of heavy-lift launch vehicles like NASA's Space Launch System, SLS, SpaceX's Starship, and Blue Origin's New Glenn allows for more mass to be transported at once, enabling the delivery of larger, more capable habitat modules. Robotic precursors can deploy infrastructure, perform construction tasks, and test environmental systems before human crews arrive. Surface mobility is supported by pressurized rovers and autonomous robotic systems that can assist with cargo handling, terrain mapping, and construction activities. One notable advantage of lunar settlement is its potential to serve as a training ground and stepping stone for deeper space missions. Establishing and maintaining a permanent presence on the Moon helps refine the technologies, operational protocols, and psychological support systems necessary for future missions to Mars or other destinations. Lessons learned from lunar living, such as maintaining habitat integrity in vacuum conditions, recycling resources, or managing crew health in isolation, can be directly applied to future endeavors. Communication infrastructure on the Moon is another essential factor for sustainability. Direct line-of-sight communication with Earth is possible from the near side of the Moon, allowing for continuous contact. For far-side operations, satellite relay networks placed in lunar orbit or at Earth-Moon Lagrange points can maintain connectivity. These systems would support not only voice and telemetry, but also remote operations, navigation, and data transfer for scientific and engineering tasks. Scientific research is expected to be a major component of early lunar life. The Moon's stable geology and lack of atmospheric interference make it an ideal platform for astronomical observatories, deep space communication arrays, and solar particle detectors. Geological studies of lunar rocks and ice deposits can also reveal information about the early solar system, Earth's history, and planetary evolution. Although initial lunar settlements will likely be small and heavily automated, expansion is expected as technology matures. With sufficient power, resources, and shielding, habitats can be enlarged to support larger populations. Over time, manufacturing facilities, greenhouses, educational centers, and medical labs could all be added. While the moon cannot replicate the Earth's ecosystem, it can offer a controlled environment capable of sustaining a segment of humanity, initially in the hundreds and potentially over many decades in the thousands. Security, safety, and redundancy will underpin every stage of lunar development. System failures in such an environment are unforgiving. Redundant airlocks, independent power circuits, backup life support, and distributed water systems will be standard. Emergency shelters and evacuation protocols must be in place for contingencies ranging from micrometeorite impacts to system malfunctions. While the moon presents one of the harshest imaginable environments for human life, vacuum, radiation, extreme temperature swings, and no atmosphere, it remains the most achievable location for beginning life beyond Earth. With current and near-future technologies, humanity can establish a controlled, modular, and increasingly self-sufficient presence there. The moon may never be home in the traditional sense, but it can become a functional habitat, a critical research base, and a launch pad for further exploration. As a first step into the solar system, it offers lessons that Earth can no longer teach. Chapter 5. Mars, the long-term hope. Among all the planets in the solar system, Mars remains the most promising candidate for long-term human habitation beyond the moon. It is similar to Earth in several important ways. It has a day length of roughly 24.6 hours, seasons due to its axial tilt, and polar ice caps made of water and carbon dioxide. It is also within reach of current or near-term rocket technology. While the moon offers a critical first step in space-based living, Mars presents the first real possibility of establishing a semi-permanent, autonomous settlement on another planet. The journey to make this a reality is complex and filled with challenges, but the scientific and technological foundation already exists to begin the transition. The average distance from Earth to Mars is approximately 225 million kilometers, though this varies with the orbital positions of the two planets. A trip to Mars using current propulsion systems, such as those planned for SpaceX's Starship or NASA's Orion spacecraft, would take between 6 to 9 months. This travel time introduces significant constraints on mission planning, cargo delivery, and crew support. Unlike the moon, which allows for real-time communication and regular resupply, Mars requires full autonomy, delayed communication, and high redundancy for all critical systems. One of the most immediate challenges of living on Mars is its thin atmosphere. The Martian atmosphere is composed of over 95% carbon dioxide, with only trace amounts of oxygen and water vapor. Surface pressure is less than 1% of Earth's, which means that unprotected humans would not survive for more than a few seconds. Habitats must be fully sealed and pressurized, with life support systems capable of maintaining temperature, humidity, oxygen concentration, and carbon dioxide removal. Fortunately, the lack of atmospheric pressure also reduces aerodynamic forces and allows for the construction of lightweight structures. Temperature regulation is another core issue. Mars is significantly colder than Earth, with average surface temperatures around -63 degrees Celsius. Temperatures can rise above freezing during the daytime near the equator, but drop rapidly at night. Habitat systems must therefore be insulated and heated, with thermal regulation built into walls, floors, and life support units. Heat can be generated using a combination of solar arrays, nuclear reactors, and potentially geothermal systems if underground heat sources are accessible. Radiation is a constant concern on Mars due to the lack of a global magnetic field and the thin atmosphere. Cosmic rays and solar particle events penetrate the Martian surface with far greater intensity than on Earth. Long-term exposure can damage human tissue, increase cancer risk, and degrade electronics. To mitigate this, habitats must be shielded using either thick layers of regolith, radiation-absorbing materials, or be constructed underground. Martian lava tubes, similar to those identified on the Moon, offer promising natural shelters that could be sealed and converted into safe habitats with minimal construction. In terms of resource utilization, Mars offers several key advantages over the Moon. The presence of water ice has been confirmed at the poles and in subsurface layers across many regions of the planet. This water can be extracted and purified for drinking, used in electrolysis to produce oxygen and hydrogen, and utilized in crop cultivation. Technologies for water extraction from ice and atmospheric moisture are already under development for lunar and Martian missions. Systems such as NASA's MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, which successfully produced oxygen from Martian CO2 in 2021, represent a major step toward localized life support. Mars also has soil rich in minerals and metals. While it lacks organic content, Martian regolith can be processed into bricks, concrete-like materials, or even used in 3D printing to create structural components. The presence of silica, iron, aluminum, and other elements supports in situ construction, which reduces the need to transport materials from Earth. With the development of automated excavation and manufacturing tools, entire habitat modules, roads, and platforms could be fabricated using native materials. Agriculture on Mars is an essential component of any long-term settlement plan. With resupply missions limited by distance and time, food production must be local and sustainable. Martian soil can potentially be conditioned for plant growth after removing toxic perchlorates and supplementing with organic matter. More realistically, in the near term, crops will be grown hydroponically or aeroponically inside sealed greenhouses with artificial lighting or filtered sunlight. These closed-loop farming systems can recycle water and nutrients, support crop diversity, and be scaled incrementally as population and demand increase. Crops like potatoes, leafy greens, and legumes are strong candidates due to their high yield and low input requirements. Energy production on Mars must be both robust and redundant. Solar panels work effectively due to the abundance of sunlight, although Mars receives only about 43% of the solar irradiance that Earth does. Solar efficiency can be hindered by dust storms, which may last for days or even weeks and obscure incoming sunlight. Energy storage solutions such as high-capacity batteries or regenerative fuel cells are therefore essential. Small nuclear reactors, particularly next-generation fission systems, provide consistent, weather-independent power and are already being developed for future deployment. NASA's Kilopower project is an example of a scalable nuclear solution that could power Martian habitats, greenhouses, and scientific outposts. Transportation on Mars requires specialized systems due to the thin atmosphere and rugged terrain. Traditional combustion engines are impractical, but electric rovers and pressurized vehicles can be deployed to transport people and cargo between sites. Mars has lower gravity, about 38% of Earth's, which allows for more efficient movement and lower energy costs for lifting materials. Aircraft such as autonomous drones or solar-powered helicopters may also be used for surveying and short-distance delivery. The success of NASA's Ingenuity helicopter in 2021 demonstrated that flight in the Martian atmosphere is possible with proper design. One major hurdle in Mars colonization is the human factor. Extended isolation, confined living, and high-stress conditions require rigorous psychological support and team dynamics. Experience gained from missions aboard the ISS and analog simulations on Earth, such as HI-SEAS, Hawaii Space Exploration, Analog and Simulation, and the Mars Society's MDRS, Mars Desert Research Station, informs the layout and operational protocols of Martian habitats. These include crew rotation schedules, distributed leadership models, and the integration of physical exercise, digital entertainment, and social activities to maintain morale. Communication between Mars and Earth is delayed by 4 to 24 minutes each way, depending on orbital positions. This time lag eliminates real-time interaction and requires significant autonomy for all systems. Mars settlers must be capable of managing equipment failures, medical emergencies, and daily operations without immediate guidance from Earth. To support this, artificial intelligence and robotics will play a central role in monitoring life support, optimizing energy usage, assisting with repairs, and ensuring safety. Scientific research will be a primary objective in early missions. Mars offers unique opportunities to study planetary geology, climate history, and the potential for past or present microbial life. Rovers and orbiters have identified sedimentary formations and mineral patterns consistent with ancient water flow. Samples collected from these areas can be analyzed in on-site laboratories or returned to Earth through future retrieval missions. Understanding Mars's history not only answers scientific questions, but also guides the selection of future settlement locations and resource targets. Mars also offers strategic advantages for the broader goal of interplanetary exploration. Its lower gravity well makes it a suitable launch point for missions deeper into the solar system. As infrastructure on Mars grows, it may one day serve as a staging ground for missions to the asteroid belt, Jupiter's moons, or even further. Building the logistical and technological backbone to support Martian life is a prerequisite for becoming a truly spacefaring civilization. Settlement on Mars will not begin with large cities, but with modular outposts housing small, specialized crews. Over time, as logistics chains mature and ISU systems improve, these outposts can be expanded into interconnected habitats, each capable of operating independently but sharing power, water, and information networks. Additive manufacturing, automated construction, and remote robotics will accelerate expansion without requiring constant human labor. Medical care on Mars will need to be as self-contained as possible. Telemedicine can provide diagnostic support from Earth, but equipment, supplies, and trained personnel must be on site for most emergencies. Facilities will include operating rooms, isolation chambers, and pharmaceutical synthesis labs to produce basic medications. Preventive healthcare will play an outsized role, supported by constant monitoring and predictive analytics. Mars is not an easy place to live. It is cold, dry, and dusty. It lacks breathable air and a protective magnetic field. Yet it is also stable, rich in resources, and reachable with the technology being developed right now. The initial steps toward living on Mars are already underway through international programs and private initiatives. What remains is the sustained commitment to develop the hardware, systems, and governance necessary to support life over the long term. Mars represents humanity's best opportunity to create a second, self-sufficient home within the solar system. It will take decades to build, maintain, and grow a functioning society there. But the foundations can be laid with tools already in development today. As Earth becomes more volatile and constrained, Mars becomes not just a destination, but a necessary continuation of human resilience and innovation. Chapter 6: Space Stations as Floating Lifeboats. In the event that Earth's surface becomes uninhabitable and other planetary bodies remain inaccessible or insufficiently developed, orbital space stations offer an immediate, scalable refuge for humanity. While not designed for large populations, space stations represent the most technologically mature form of extraterrestrial habitation. They are already in operation, proven in functionality, and continuously evolving through new research and engineering advancements. These floating platforms can serve as critical lifeboats, housing essential personnel, data archives, and infrastructure, while larger-scale relocation efforts are prepared. Living in orbit offers several benefits in scenarios where remaining on Earth is no longer viable. Space stations are positioned above the planet's atmosphere, protected from many surface-level catastrophes such as extreme weather, ground-based warfare, or biological contamination. Unlike surface environments, which are constrained by geography, orbital habitats can be stationed at specific altitudes and inclinations for optimal exposure to solar power, communication, and resource access. They also benefit from microgravity, which allows for unique manufacturing and medical research applications not possible on planetary surfaces. The most prominent example of an operational orbital habitat is the International Space Station, ISS, a collaboration between NASA, Roscosmos, ESA, JAXA, and CSA. Since November 2000, the ISS has supported continuous human presence in space, validating many of the life support, energy, and structural systems required for off-world living. Its modular design allows for expansion, reconfiguration, and the integration of new technologies over time. Lessons learned from the ISS provide the foundational blueprint for larger and more autonomous platforms. Current space station systems rely on a range of subsystems for life support, including atmospheric control, water purification, thermal regulation, and waste recycling. Oxygen is typically generated via electrolysis of water, while carbon dioxide is removed using solid amine or lithium hydroxide scrubbers. Water is reclaimed from urine, sweat, and humidity through multi-stage filtration and distillation units. While not perfect, these systems can sustain crews of up to 6 people indefinitely with only occasional resupply. Continued miniaturization, automation, and closed-loop optimization are enabling new designs that support larger populations with higher reliability. Energy in orbital habitats is primarily supplied by photovoltaic solar arrays. Modern, high-efficiency solar panels mounted on gimbaled structures track the sun to maximize output during each 90-minute orbit of the Earth. Energy storage is achieved using lithium-ion battery packs that provide continuous power through eclipse phases. Advanced models are exploring regenerative fuel cells and hybrid systems that combine solar and chemical storage for longer autonomy and increased load capacity. Radiation shielding remains a major concern in low Earth orbit and beyond. Earth's magnetic field provides partial protection against solar and cosmic radiation, but prolonged exposure still presents health risks. Existing space station modules use aluminum hulls and internal water tanks as passive shields, while newer designs incorporate polyethylene-based materials with superior hydrogen content for blocking high-energy particles. Placement in higher orbits or cislunar space will require more robust protection, including the use of artificial magnetic fields or dedicated radiation shelters within the station. Space station expansion is being actively pursued by government and commercial entities alike. NASA's Gateway Station, set to orbit the Moon, will serve as a staging point for lunar missions and potentially for Mars expeditions. Commercial efforts such as those from Axiom Space, Blue Origin, and Northrop Grumman envision orbital platforms for research, tourism, and manufacturing. These next-generation stations are modular, inflatable, and built with autonomy and scalability in mind. Inflatable modules, like Bigelow Aerospace's Beam prototype, offer high volume-to-mass ratios and can be deployed with minimal launch footprint. Manufacturing in microgravity is another crucial advantage of orbital habitats. Processes that are difficult or impossible on Earth, such as the formation of perfect crystals, fiber optics with fewer defects, or the layering of bioprinted tissues, are enhanced in weightless environments. These capabilities support not only the internal sustainability of space stations, but also provide valuable materials and components that can be shipped to Earth or other locations in space. Orbital farms are under development to supplement food supply for long-duration missions. Hydroponic and aeroponic systems are already being tested on the ISS, with crops such as lettuce, radishes, mustard, and wheat demonstrating successful growth cycles. Light-emitting diode arrays tuned to specific wavelengths support plant growth with minimal energy input. Waste biomass is composted or processed into growing medium, contributing to closed-loop agricultural systems that reduce dependency on resupply from Earth. Waste management is managed through controlled incineration in Earth's atmosphere for non-recyclable material or repurposing for secondary functions. Some organic waste is composted for agriculture, while water waste is processed and reused. Urine and condensate are filtered and chemically treated to produce potable water, while solid waste is either compressed and stored or packed for disposal during scheduled cargo returns. Orbital stations must maintain constant attitude control and propulsion capability to avoid orbital decay and collisions with space debris. This is typically achieved through gyroscopic stabilization, reaction wheels, and thruster burns using hydrazine or ion engines. Continuous tracking of debris via ground-based radar and satellite systems enables course adjustments to prevent damage. In the event of an imminent collision, stations execute avoidance maneuvers to reposition safely. Communication infrastructure in orbit is robust and fast. Stations use high-frequency radio links, laser communication relays, and satellite-based networks to maintain near-continuous contact with Earth. For habitats further from Earth, such as lunar or Lagrange point stations, delay-tolerant networking and autonomous operation protocols are essential. These allow data to be prioritized, stored, and transmitted when windows become available. Crew selection for orbital life is based on medical, psychological, and technical criteria. Astronauts are trained in maintenance, emergency response, scientific operation, and extravehicular activity, EVA. In future scenarios where long-term or even indefinite habitation is required, station populations may include specialists beyond traditional astronauts, engineers, agronomists, medics, and system designers capable of maintaining all aspects of life support and infrastructure. In the event of a surface collapse on Earth, orbital stations could serve as observation posts, communication relays, and even command centers for coordinating evacuation or supply missions to underground, oceanic, or lunar habitats. They would also act as data preservation hubs, storing digital backups of human knowledge, cultural artifacts, and scientific repositories. Their isolation from Earth-based disasters makes them ideal for continuity of government operations, scientific monitoring, and strategic planning. Population limitations are the most significant bottleneck for space station-based survival. Current stations can support only a handful of people at once. However, scaling is theoretically straightforward. With expanded launch capability from rockets like SpaceX's Starship or Blue Origin's New Glenn, large structural components can be deployed and assembled in orbit using automated robotic arms or human EVA. Over time, orbital stations could grow into full-blown space habitats, hosting hundreds or thousands of people if sufficient infrastructure is developed. Artificial gravity is often discussed as a long-term solution for microgravity health effects. While currently impractical in most operational designs, rotating habitats or tethered modules creating centripetal force could become part of future station upgrades. Until then, physical countermeasures like resistive exercise, dietary management, and bone density monitoring will be essential for maintaining crew health over multi-month or multi-year durations. Redundancy is essential in every system on board a space station. From duplicate power circuits and water filters to backup oxygen generators and fire suppression systems, the environment demands high fault tolerance. Emergency procedures include isolation of compromised modules, rapid evacuation into escape vehicles such as crew capsules or automated return vehicles, and real-time support from ground control. Training for all scenarios from depressurization to equipment fire is continuous and rigorous. Space stations may also serve as waypoints in a larger orbital network. Placed at different altitudes and inclinations, they can relay information, support cargo exchange, and function as assembly yards for larger spacecraft. The concept of orbital shipyards, where interplanetary vessels are constructed or refueled before departure, is already under development in multiple space programs. The eventual evolution of space stations into large-scale orbital habitats, such as O'Neill cylinders or Stanford toruses, is a longer-term vision. These concepts involve rotating structures several kilometers in length, with simulated gravity, internal weather systems, and full-scale agriculture. While these remain in the design phase, their physical feasibility has been established. The transition from compact modules to rotating habitats is a matter of engineering scale and economic will, not fundamental science. In the nearer term, space stations will serve as critical nodes in the survival architecture of humanity. They offer autonomy, protection, communication, and mobility, all above the dangerous and unpredictable conditions developing on Earth's surface. Whether occupied by researchers, engineers, decision-makers, or caretakers of vital data, orbital stations will form a thin but resilient line of continuity between the civilization that was and whatever comes next. Chapter 7. Living on Titan, the most Earth-like world that isn't. Among the many destinations in the solar system that could one day support human life, Titan stands out as a uniquely intriguing possibility. As Saturn's largest moon, Titan is the only moon known to possess a thick atmosphere and stable bodies of liquid on its surface. These two characteristics alone distinguish it sharply from most other celestial bodies in the solar system. While inhospitable by Earth standards, Titan shares enough environmental parallels, atmospheric pressure, climate cycles, and surface liquids, that scientists have identified it as one of the most Earth-like worlds, albeit in a frigid and chemically alien form. Titan orbits Saturn at a distance of approximately 1.2 billion kilometers from the Sun. This vast distance places it well beyond the traditional boundaries of the inner solar system, making travel to Titan a major challenge. At current technological levels, reaching Titan would require a journey lasting 6 to 8 years, using chemical propulsion systems, though future nuclear, thermal, or electric propulsion technologies could reduce this significantly. Despite the long travel time, Titan's features have drawn the attention of astrobiologists, planetary scientists, and engineers alike, not as a short-term target, but as a viable site for long-term scientific exploration and potentially even colonization. Titan's most notable feature is its dense atmosphere. Composed primarily of nitrogen with small amounts of methane and hydrogen, Titan's atmosphere is roughly 1.5 times the pressure of Earth's at sea level. This provides natural protection from radiation, something that Mars and the Moon notably lack. Cosmic rays and solar ultraviolet radiation are significantly attenuated before reaching the surface, reducing the need for extreme shielding in surface habitats. While the atmosphere is unbreathable and extremely cold, it offers a degree of environmental stability that is rare elsewhere beyond Earth. The surface temperature on Titan averages around 179 degrees Celsius. At this temperature, water is as hard as rock and methane exists in liquid form. Titan has a full hydrological cycle: clouds, rain, rivers, lakes, and seas, though based not on water, but on hydrocarbons. Its lakes and seas are primarily composed of liquid methane and ethane, collected in vast basins across the polar regions. Radar imagery from NASA's Cassini mission revealed shoreline patterns, river networks, and even evidence of seasonal weather, such as methane rainstorms and shifting cloud cover. While the presence of these hydrocarbons rules out any direct use for human hydration or agriculture, they provide an abundant local source of energy. Methane can be processed into fuel using well-understood chemical methods, and hydrogen, also present in small quantities, may be extracted for energy storage or propulsion. The idea of fuel from the ground makes Titan a self-sustaining outpost for chemical energy, provided that the necessary reactors and processing systems are brought or built in situ. The atmospheric pressure on Titan allows for relatively straightforward engineering of surface habitats. Unlike the Moon or Mars, where pressure differentials between the habitat interior and the outside environment are extreme. Titan's external pressure is high enough to simplify structural demands. Habitats would not require the same level of reinforcement as in near-vacuum environments. The extreme cold, however, requires high-performance thermal insulation and heat retention systems. Most materials used in terrestrial construction become brittle at Titan's temperatures, so specialized alloys, polymers, and composites designed for cryogenic stability would be essential. Habitats on Titan would likely be pressurized domes or buried modules, heated internally using nuclear or radiothermal sources. Electric power could be generated using compact fission reactors, as solar energy is impractical due to the great distance from the sun and the dense, hazy atmosphere that blocks most visible light. Solar irradiance at Titan's surface is only about 1/100th that of Earth's. Consequently, photovoltaics would require prohibitively large surface areas for modest output. Nuclear power offers consistency, longevity, and compact design, well suited for cold, remote environments like Titan. Titan's surface is composed of icy bedrock and organic-rich sediments. The crust is believed to be primarily frozen water, possibly overlaying a subsurface ocean of liquid water mixed with ammonia. The potential existence of this subsurface ocean raises interest in the possibility of microbial life, or, at minimum, usable liquid water that can be extracted through melting and purification. Water, while not available on the surface in liquid form, may be accessible through drilling or thermal excavation. If reachable, it could serve not only for hydration, but also for oxygen production through electrolysis. Building materials on Titan may also be sourced locally. Ice, while brittle in Earth's climate, behaves more like rock at Titan's temperatures and can be cut, stacked, or fused into structures. With appropriate treatment, ice-based composites could be used for shelter, radiation shielding, or insulation. Hydrocarbons on the surface, in solid and liquid form, can be refined into polymers and fuels. If equipment for chemical synthesis is available, Titan's organic-rich environment becomes a source of plastic-like materials for construction, tools, and containment vessels. Mobility on Titan offers unique opportunities. Due to the dense atmosphere and low gravity, only 14% that of Earth, it is theoretically possible to fly using minimal lift energy. Balloons, gliders, and rotorcraft could easily navigate the thick air, offering low-energy methods of surface exploration. Concepts have been proposed for floating scientific platforms and aerial drones capable of long-distance travel, powered by small onboard energy sources. Even crewed aircraft could become viable with moderate energy inputs, creating a network of mobile habitats or cargo systems that move between locations. From a psychological and operational standpoint, Titan presents both benefits and challenges. The thick haze that blankets the moon means that the sky is never truly clear, and there is no direct line of sight to the stars or to Saturn itself from most ground positions. While this reduces exposure to harmful radiation, it also limits access to natural light and vistas, which are beneficial for mental health. Habitat interiors would need to simulate day-night cycles and incorporate biophilic design elements to promote psychological well-being. Lighting, colors, and environmental controls would play a major role in maintaining a stable and healthy living environment. Communication with Earth from Titan experiences a signal delay of over an hour one way. Real-time communication is not possible, necessitating autonomous systems for navigation, diagnostics, and local decision-making. Data relay satellites orbiting Saturn or Titan could support periodic uploads and downloads. Crew members would be trained to operate independently, troubleshoot problems, and manage mission-critical systems without immediate support from mission control. Agriculture would require completely closed systems. Crops could be grown hydroponically under artificial light inside heated and pressurized greenhouses. Nutrient cycling, water reclamation, and pollination would need to be fully managed. Waste from the crew and uneaten biomass would be processed into fertilizer or biogas. Due to the absence of sunlight and native soil, food production would be entirely mechanical and energy-intensive, but manageable with current or near-future technology. Scientific research would be central to any early mission. Titan offers a unique environment to study organic chemistry, planetary weather, and astrobiological potential. Its atmosphere contains complex hydrocarbons that mimic conditions on the early Earth. By analyzing atmospheric reactions and surface chemistry, scientists can gain insights into prebiotic processes that may have led to life. If a subsurface ocean is confirmed and accessed, its composition could reveal whether Titan harbors microbial ecosystems, or at the very least, the ingredients for life. Logistically, missions to Titan would involve periodic launches from Earth, or possibly from Mars or lunar stations, depending on future infrastructure development. Due to the travel time and energy cost, resupply would be infrequent and must be planned with extreme precision. Autonomous cargo vehicles, long-duration storage modules, and redundant systems would be used to mitigate delays. Over time, a small population of researchers, engineers, and support personnel could rotate in and out of a central station, expanding capacity gradually as systems prove reliable. In the far future, a Titan base could evolve into a fully autonomous outpost with permanent inhabitants. With advancements in closed-loop life support, in-situ manufacturing, and robotic maintenance, human presence on Titan could be sustained indefinitely. The station could act as a fuel depot for missions deeper into the solar system, a research hub for cryogenic chemistry, and a symbol of humanity's ability to adapt to extreme environments. Though remote and harsh, Titan holds the potential to become one of the most important outposts for humanity's long-term survival. Its atmosphere, chemistry, and geology make it unique among moons and planets. While it may never support open-air living or large-scale migration, Titan could serve as a stable, energy-rich, and scientifically valuable base, one that proves our species can not only leave Earth, but build a future far from its warmth and light. Chapter 8. Beneath the ice of Enceladus. Among the many icy moons of the outer solar system, Enceladus stands out as one of the most scientifically compelling and one of the most promising environments for potential extraterrestrial life. Though only about 500 kilometers in diameter, this small moon of Saturn has captivated planetary scientists since NASA's Cassini mission revealed geysers erupting from its southern polar region, spraying water vapor and organic molecules into space. Beneath Enceladus's frozen crust lies a global subsurface ocean kept warm by tidal heating, an energy source that may support chemical processes similar to those found in Earth's deep oceans. These findings position Enceladus not just as a target for exploration, but as a plausible, long-term habitat for humans seeking refuge in the outer solar system. Living on Enceladus would be unlike habitation on any planetary surface or orbital station. The environment above the ice is harsh and inhospitable. The surface temperature hovers around 200 degrees Celsius, and there is no atmosphere to speak of, only a thin exosphere composed of water vapor and trace gases. Solar irradiance is nearly 100 times weaker than on Earth, rendering traditional solar power systems largely ineffective. Radiation levels around Enceladus, while lower than those near Jupiter's moons, are still significant due to Saturn's magnetosphere. Despite these challenges, the moon's unique internal ocean and relative proximity to Saturn's ring system offer opportunities for scientific discovery, resource extraction, and possibly long-term settlement using highly specialized technology. The most intriguing feature of Enceladus is its internal ocean, estimated to lie beneath an ice shell 20 to 40 kilometers thick. Though the ice is believed to be much thinner, possibly only a few kilometers, at the South Pole. There, the so-called tiger stripes fissures release plumes of water vapor and ice particles from subsurface reservoirs. These plumes not only feed Saturn's E-ring, but also serve as natural vents from the internal ocean, allowing researchers to sample its composition without the need for deep drilling. Cassini's analysis of the plumes found organic compounds, salts, silica nanoparticles, and molecular hydrogen, all ingredients that suggest hydrothermal activity on the ocean floor. On Earth, similar conditions support entire ecosystems independent of sunlight, thriving around hydrothermal vents where chemical energy drives life processes. Establishing a habitat on Enceladus would require avoiding the surface and instead operating below the ice, where conditions are more stable and better shielded from radiation. The primary challenge is accessing the ocean. One approach involves deploying heat-propelled cryobots capable of melting through the ice crust while carrying communication tethers and scientific instruments. These cryobots would need to navigate complex ice layers, maintain directional control, and manage refreezing behind them. Once they reach the ocean, autonomous submersibles, hydrobots, could be deployed to explore, map, and sample the liquid environment. To make this viable for human habitation, the entrance zone would need to be stabilized and expanded into a sealed access shaft. A series of airlocks and pressure buffers would allow personnel and equipment to move between the subsurface habitat and the ice tunnel. Habitats themselves could be either suspended in the ocean, anchored to the ice ceiling, or constructed on the ocean floor if conditions permit. Each option requires overcoming unique challenges related to pressure management, thermal control, and biosecurity. Water provides an inherent radiation shield, so a habitat suspended beneath kilometers of ice would be naturally protected from cosmic rays and solar particles. This is one of Enceladus's most significant advantages over surface-based settlements elsewhere in the solar system. Temperature control is a secondary benefit, as the ocean is kept near the freezing point of water by internal geothermal heating. This reduces the extreme temperature differentials seen on planetary surfaces or in orbit. Power generation for an Enceladus habitat would likely rely on compact fission reactors. These systems can operate continuously and produce sufficient energy for heating, life support, lighting, and industrial processes. While traditional solar panels are impractical due to weak sunlight and heavy ice coverage, nuclear systems provide the stability needed for multi-decade operations. Waste heat from the reactor could also be used to maintain temperature in the access shaft and melt water for use in the habitat. Life support systems would follow a closed-loop design. Water is abundant and easily processed for drinking, hygiene, and oxygen production via electrolysis. Atmospheric control systems would manage carbon dioxide levels, humidity, and airborne contaminants using chemical scrubbers and filters similar to those tested on the International Space Station. Food production would take place in hydroponic or aquaponic farms under artificial lighting. With energy efficiency being critical, LED systems would be tuned to the most photosynthetically active wavelengths. Protein sources might include cultured fungi, insect-based systems, or aquaponics if edible fish species can be sustained in closed environments. Waste recycling would be essential. Organic waste can be composted into fertilizer or converted into biogas through anaerobic digestion. Non-organic waste would be repurposed when possible or stored for return to orbital facilities. The limited supply lines between Enceladus and any support base, whether in Saturn orbit or on Titan, mean that resupply missions would be infrequent and focused on critical items such as specialized tools, electronics, or rare compounds not available locally. Enceladus's low gravity, approximately 0.011 grams, introduces both advantages and health risks. On one hand, low gravity allows for easier transport of materials, the use of lighter construction components, and reduced mechanical stress on equipment. On the other hand, extended exposure to low-gravity environments causes muscle atrophy, bone density loss, and potential cardiovascular changes in humans. Mitigation strategies would include resistance-based exercise equipment, centrifuge-based artificial gravity habitats, and pharmaceuticals aimed at preserving musculoskeletal health. Establishing a presence beneath Enceladus's ice would likely involve a multi-phase mission plan. The first phase would focus on robotics scouting, including cryobot tests, plume sampling, and seismic mapping to identify optimal entry points. The second phase would involve autonomous cargo delivery and shaft construction using robotic drills or thermal penetrators. Only once systems have been validated and redundancy established would human crews descend to begin construction and inhabit the ocean base. These crews would likely live in shifts of 6 months to a year, similar to current operations on the ISS, until a sufficient infrastructure allows for permanent rotation or self-sufficiency. A subsurface habitat on Enceladus could support a population of scientists and engineers focused on astrobiology, oceanography, and planetary geology. The unique opportunity to explore an alien ocean without ever having to land on the ocean's surface allows Enceladus to act as a gateway to understanding how life might evolve in other star systems. Experiments could include biochemical analysis of hydrothermal vent regions, microbial culturing from vent plumes, and long-term monitoring of ocean chemistry and pressure dynamics. Submarines equipped with mass spectrometers, cameras, and sonar would navigate the underwater terrain, mapping seafloors, ice boundaries, and mineral-rich formations. Communication with the outside world would require relays positioned in orbit around Enceladus or Saturn. Due to the thick ice and liquid layers, direct communication from the subsurface to Earth is impossible without intermediary stations. High-bandwidth lasers or radio transmitters positioned on the surface or in orbit would handle data uploads, while internal systems rely on fiber optic lines and local wireless networks for crew coordination and robotic control. Enceladus would not be colonized for its convenience, but for its potential. Its inaccessibility and distance from Earth make it impractical for large-scale migration, but its internal ocean offers a rare and valuable environment for research and technological development. It could serve as a model for future missions to other icy worlds, such as Europa, Ganymede, or even exoplanets orbiting far-off stars. Its isolation, while extreme, creates a natural laboratory for advancing autonomous operations, biosecurity protocols, and self-reliant ecosystems. Over time, with enough technological refinement, a subsurface colony on Enceladus could expand. Modular habitats could be linked together via pressure tunnels. Vertical farming towers could be suspended in thermal zones, optimizing energy efficiency. Specialized robotic teams could maintain ice walls, remove biofouling from equipment, and monitor for tectonic activity. Power, waste, and atmospheric systems would be controlled by centralized AI systems, with human oversight focused on science, maintenance, and mission planning. The experience of surviving beneath the ice of Enceladus would likely transform the way humans think about habitability itself. Here, in the complete absence of sunlight and atmospheric pressure, surrounded by ice and darkness, humans could build a stable and secure outpost using only the heat from tidal flexing, the chemistry of water and rock, and the ingenuity of modern engineering. If Earth's surface is ever lost to disaster, these skills may become essential, not just for research, but for survival. Chapter 9. Cities in the Rings of Saturn. Saturn's rings are among the most iconic and visually arresting features in the solar system. Composed primarily of water ice with traces of rock and dust, they stretch over 280,000 kilometers in diameter, yet are incredibly thin, often just tens of meters thick in many places. To the naked eye, they appear solid and smooth, but in reality, they are made up of countless individual particles ranging in size from grains of sand, to house-sized boulders, all orbiting Saturn in a delicate gravitational dance. These rings have fascinated astronomers for centuries, but recent advances in space habitat engineering raise a provocative question. Could humans one day live among them? The concept of building settlements in Saturn's rings may seem like pure science fiction, but when approached through the lens of orbital physics and habitat engineering, it becomes an intriguing thought experiment grounded in scientific possibility. Saturn itself is not habitable. It is a gas giant with no solid surface, extreme atmospheric pressures, and fierce weather systems. However, its orbital environment offers unique advantages, particularly in terms of solar exposure, gravitational stability, and access to raw materials. The idea of establishing cities, or at least permanent orbital habitats, within or adjacent to the rings requires reimagining the relationship between human settlement and orbital mechanics. The rings themselves are not suitable for direct construction. Their constant motion and density variations make them a dynamic and unstable environment. Any structure attempting to rest on the rings would quickly be destroyed by impacts with particles moving at thousands of kilometers per hour. Instead, the key lies in co-orbital placement, constructing space habitats that orbit Saturn in synchrony with ring segments, but remain slightly above or below the densest ring planes to minimize collision risk. These habitats would not be in the rings per se, but embedded in their environment, sharing their orbital path while avoiding direct contact. Orbital habitats positioned in this manner could benefit from Saturn's gravity and the gravitational effects of its moons, which help to maintain stable orbital corridors known as shepherd zones. These regions are already responsible for the maintenance of gaps and edges within the ring system. By positioning habitats in these naturally stable regions, engineers could exploit existing orbital dynamics to reduce station-keeping energy costs and maintain long-term positional stability. These orbital habitats would resemble advanced versions of current space station designs, such as modular stations with rotating sections to simulate artificial gravity through centrifugal force. While zero gravity can be managed with exercise and pharmaceuticals, long-term habitation requires gravity-equivalent forces to avoid physiological degradation. A rotating torus, O'Neill cylinder, or other artificial gravity system could be used to provide a comfortable environment for residents. These habitats would need to be heavily shielded from radiation and micrometeoroid impacts, both of which are persistent threats in Saturn's orbit. Radiation is a serious concern in the vicinity of Saturn. The planet's magnetic field traps energetic particles from the solar wind, forming radiation belts that are dangerous to humans. Habitats would require extensive shielding, using materials such as polyethylene, water, or regolith-derived blocks to attenuate high-energy particles. In some concepts, shielding could be enhanced by incorporating electromagnetic deflection systems, or by positioning habitats in regions of lower radiation intensity, possibly near the equatorial gaps between the rings where particle flux is reduced. Power generation in Saturn orbit is complicated by the reduced solar irradiance, only about 1% of what Earth receives, but it remains feasible. Large-area photovoltaic arrays, optimized for low-light conditions and equipped with solar tracking, could supply baseline electrical power. Alternatively, and perhaps more realistically, compact nuclear fission reactors would provide consistent energy output regardless of sunlight availability. These reactors would need to be heavily shielded and mounted away from residential areas of the habitat, either on tethers or separate modules. One of the most compelling advantages of this orbital region is the abundance of raw material. The ring system is composed mainly of water ice, which can be harvested and refined into drinking water, breathable oxygen, and hydrogen fuel. Automated mining drones or electromagnetic collection scoops could gather ring particles and deliver them to processing stations on orbiting platforms. These stations would separate materials using heat, centrifugation, and electrolysis, feeding the life support and propulsion systems of the habitat. Construction of such cities would be performed in stages. Initial robotic missions would map orbital dynamics, identify collision risks, and test autonomous maintenance systems. Once safe and stable orbital bands are identified, robotic assemblers could begin building infrastructure, docking platforms, communication arrays, solar farms, and structural frames. Human crews would follow in heavily shielded transports, tasked with activating and overseeing core systems such as life support, habitat assembly, and energy generation. Over time, the habitat would expand modularly, adding new residential zones, research labs, agriculture domes, and industrial compartments. Agriculture in orbit around Saturn would be conducted within pressurized and temperature-controlled biospheres. Hydroponic farms, aeroponic systems, and bioreactors would produce food for the population. LED lighting arrays would simulate solar cycles for plant health, and waste products would be composted or converted into biofuel. In a fully closed-loop system, human and plant metabolism would be synchronized to recycle carbon dioxide, water, and nutrients efficiently. Protein could be sourced from algae, lab-grown meat, or aquaculture systems, depending on available water and energy. Transport between ring habitats and other parts of the Saturn system, such as Titan or Enceladus, would rely on efficient transfer orbits using ion propulsion or low-thrust chemical engines. These intermoon routes would be serviced by reusable shuttles designed to carry cargo and personnel across the planetary system. Each habitat would also maintain emergency escape vehicles capable of quickly exiting Saturn orbit and initiating a return trajectory to Earth or a lunar way station in the event of critical failure. Communication systems would need to be robust and redundant. Signals between Saturn and Earth face significant delays, averaging about 70 to 90 minutes round trip, necessitating high degrees of local autonomy. Habitats would maintain a network of laser communication relays and radio antennas for inter-habitat coordination, surface interaction with robotic outposts, and scheduled data uplinks to Earth. Emergency communication would be prioritized and compressed, while non-critical data could be batch transmitted during optimal windows. In the long term, multiple habitats could be linked together into large orbital megastructures, forming rotating colonies with thousands of residents. These cities would be supported by integrated utilities, resource harvesting satellites, and manufacturing platforms that use local materials to produce tools, replacement parts, and construction components. Additive manufacturing would be heavily utilized, reducing dependence on shipments from Earth. Complex systems could be fabricated using pre-mined silicates and metals from captured asteroids or ring material. The psychological environment of life among Saturn's rings would be unlike anything experienced by humans so far. With Saturn dominating the sky and the rings stretching endlessly beyond the viewport, residents would live with a continuous awareness of their place in a vast and dynamic environment. Artificial windows and projection domes would replicate Earth-like views for mental health, but it's likely that new cultural and social norms would emerge, shaped by life in a rotating habitat, distant from planetary surfaces, and governed by the rhythms of orbital mechanics. Although the engineering and logistical challenges are considerable, the establishment of human settlements in Saturn's ring plane is not beyond the realm of technological possibility. The required tools, autonomous robotics, artificial gravity habitats, advanced life support, nuclear energy systems, and in-situ resource utilization are already being developed or tested in Earth orbit and lunar programs. Scaling them to Saturn's distance is a question of propulsion capability and long-term investment, not fundamental feasibility. Ring-based habitats would not only expand the reach of humanity, but also redefine what constitutes a living space. Detached from planetary surfaces, free from atmospheric constraints, and immersed in a constantly shifting belt of ice and light, these cities could represent the most profound transformation in human architecture since the development of spaceflight itself. They would be dynamic, evolving communities shaped by orbital geometry and technological adaptation, proof that even among the cold debris of ancient moons and shattered comets, life can persist and even flourish. Chapter 10. Neptune's moon Triton, our final outpost. At the outermost frontier of our solar system lies Triton, the largest moon of Neptune. Cold, distant, and enigmatic, Triton stands as one of the most intriguing candidates for deep space habitation, not for its convenience or resource abundance, but for its potential to serve as humanity's final outpost, an observatory, a sentinel, and a stronghold far from the turbulence of the inner worlds. If Earth becomes uninhabitable and all nearer refuges are compromised, Triton may represent the most remote fallback location that could be reached and sustained using technology that is now emerging or on the near horizon. Triton is not like the other large moons in the solar system. It is unique in several fundamental ways. It is one of the few large bodies that orbits its planet in a retrograde direction, meaning it moves opposite Neptune's rotation, suggesting it was likely captured from the Kuiper belt. This origin gives it a composition more similar to icy dwarf planets like Pluto than to traditional moons. Triton is also geologically active despite its extreme cold, with cryovolcanoes, resurfaced plains, and indications of a subsurface ocean beneath its icy crust. It is a dynamic environment, albeit one unfolding on timescales and conditions far removed from those of Earth. Reaching Triton presents one of the most significant challenges in solar system exploration. At over 4.3 billion kilometers from Earth, a direct mission would take over a decade using current propulsion systems. The only spacecraft to ever visit Triton was Voyager 2 in 1989, which provided the first and only close-up images of the moon. Since then, no missions have returned, although proposals for orbiters and landers continue to surface. However, should a long-term strategy for deep colonization emerge, Triton's characteristics make it a serious candidate for consideration. The surface temperature on Triton hovers around -235°C, making it one of the coldest objects in the solar system. This is due both to its distance from the Sun and its high albedo. Its surface reflects much of the already limited sunlight it receives. As a result, solar energy is effectively useless for sustaining human activity. Power would need to be supplied by nuclear sources, such as compact fission reactors or future fusion systems. These reactors would serve as the foundation of any settlement, providing heat, electricity, and propulsion energy in a compact and reliable form. Triton's atmosphere is extremely thin and composed mainly of nitrogen with trace amounts of methane. Although unbreathable and insufficient for shielding or pressure, this atmosphere does indicate active surface and subsurface processes. Winds blow across frozen plains, moving nitrogen ice and shaping the terrain into ridges and scallops. Geysers have been observed ejecting nitrogen gas and dark dust particles several kilometers into the sky, suggesting internal heat and dynamic geological activity. Any human habitat on Triton would need to be heavily insulated, fully pressurized, and located either beneath the surface or within specially shielded domes. Surface habitats would be subjected to extreme cold, micrometeorite impacts, and radiation from galactic cosmic rays, as Neptune lacks a protective magnetic field comparable to Earth's. Subsurface construction, similar in concept to lava tube shelters proposed for the Moon and Mars, would offer better shielding and thermal insulation. Drilling into Triton's crust to access these cavities or artificially excavating ice tunnels would likely be necessary. The composition of Triton's crust and interior offers both opportunities and challenges. Its surface is made primarily of water ice mixed with nitrogen, carbon monoxide, and methane ices. These materials can be harvested and processed into usable resources. Water can be melted and purified for drinking and hydroponic agriculture. Electrolysis of water provides breathable oxygen and hydrogen for fuel. Nitrogen and methane, when processed correctly, can support the manufacture of plastics, fertilizers, and even propellants, such as methane-based rocket fuel. Triton's low gravity, only about 8% of Earth's, reduces the energy cost of lifting and transporting materials across its surface and into orbit. Construction, cargo deployment, and emergency evacuation would all benefit from the minimal gravitational constraints. However, extended exposure to such low gravity is harmful to human physiology. As with other low-gravity environments, countermeasures would include intensive exercise regimens, pharmacological support, and possibly centrifuge-based living quarters that simulate partial gravity through rotation. Because of its retrograde orbit and distance from Neptune, Triton is slowly spiraling inward toward the planet. In several billion years, it is expected to either crash into Neptune or break apart and form a new ring system. However, this process is so gradual that it presents no threat within any realistic human timeframe. In the interim, the Moon remains a stable, tidally locked body with a known orbit and predictable surface dynamics. Transportation to and from Triton would be a rare and high-cost endeavor. Missions would need to be launched during optimal planetary alignments, taking advantage of gravitational assists and high-efficiency propulsion systems. Nuclear electric propulsion or advanced ion engines would be essential for cargo and personnel transit. Once infrastructure is established, a fleet of long-range interplanetary vessels could maintain a logistical corridor between Triton and other solar system nodes, albeit with travel times measured in years. Communication with Earth from Triton introduces a latency of over 8 hours round trip. This prohibits real-time dialogue and requires significant onboard autonomy for all systems. Artificial intelligence would play a central role in habitat management, scientific research, and emergency response. Crew members would be trained in a wide array of disciplines to minimize reliance on Earth-based support, with on-site manufacturing, 3D printing, and recycling systems enabling a high degree of self-sufficiency. Habitat interiors would be designed to support long-term psychological health under conditions of extreme isolation and darkness. Artificial lighting systems would replicate Earth-like day-night cycles. Environmental controls would regulate temperature, humidity, and air quality. Walls might be equipped with interactive surfaces displaying images of Earth, nature, or simulated outdoor environments. Social structure would emphasize cooperation, routine, and shared purpose, reinforced through virtual interaction with other habitats across the solar system. Scientific research would be a core function of any Triton outpost. One of the most important objectives would be the study of its suspected subsurface ocean. If confirmed, this ocean would be kept liquid by tidal heating, similar to those beneath the crusts of Europa and Enceladus. Drilling into the crust to access this ocean would allow scientists to analyze its composition, search for microbial life, and study its potential for habitability. Instruments would need to be sterilized to prevent contamination, and samples would be examined using biosafety protocols comparable to those used in planetary protection labs on Earth. Geological studies would also yield insights into Triton's origin, evolution, and internal processes. As a captured Kuiper Belt object, Triton may offer clues to the early history of the solar system and the distribution of organics in the outer regions. Surface mapping, seismic monitoring, and cryovolcanic analysis would deepen understanding of this moon's geophysics. Combined with atmospheric studies and magnetometer readings, these efforts would contribute to broader models of planetary and moon formation. Given Triton's remote position, it could also serve as an observatory platform for deep space astronomy. The absence of atmospheric interference, low thermal noise, and isolation from artificial light make it an ideal site for infrared and radio telescopes. Orbiting observatories could be constructed in tandem with the surface habitat, relaying data to Earth or intermediate outposts. In the distant future, if interstellar probes are launched, Triton could become one of the last refueling or data handoff stations before they depart the solar system entirely. Triton's harsh environment ensures that colonization would be limited to small, specialized teams for the foreseeable future. However, as technology progresses, the settlement could expand into a hub of deep space research, energy generation, and autonomous industry. With the proper support systems, it could support rotating crews, host international scientific collaborations, and function as a beacon of resilience at the edge of the known world. Its role in human history would be profound, not as a thriving metropolis, but as a symbol of persistence and exploration. On a moon where the sun appears no brighter than a distant star, humanity could establish a foothold, adapt to conditions entirely unlike those on Earth, and prove that even in the coldest and darkest corners of the solar system, life can still organize, learn, and endure. You've now traveled through every possible refuge humanity might find if Earth could no longer sustain us. From deep beneath the ice, to the rings of Saturn, to the final outpost in the dark beyond Neptune. If you're still awake and your mind is still wandering, I invite you to explore another of our sleep-inducing journeys. Perhaps a quiet voyage through the structure of the universe, or a gentle exploration of strange cosmic phenomena. But if your eyes are closing and your thoughts are floating away, then rest well. The universe is vast. Good night and sweet dreams among the stars.